So can we maybe tie this back to 19% and 22% in our portfolio weights? And unfortunately, this is a little bit more complicated, and we have to introduce another variable first that we're going to use in this computation. And this variable is called the correlation. So we're going to use the correlation coefficient between those two variables in the formula. So let me first define you what a correlation is. That's the middle formula here. So the correlation coefficient, that's abbreviated with the Greek letter rho, is basically the covariance between the two variables, but before you compute the covariance, you divide by the standard deviation of each variable. So it's a standardized covariance in that sense. And by the way, since the volatilities here are constants, you can actually take this out of the formula. So you can rewrite this also as the covariance between the two variables. And divide by the individual volatilities. And this here is the Greek letter rho. Now, what's the benefit of using the correlation coefficient over the covariance? The correlation coefficient has a very nice interval. It's always between -1 and +1. Right? So, and always, for any two variables that you measure, it will always be in that range. And these values have kind of meanings to it. So if the correlation coefficient is exactly +1, and those two variables are perfectly correlated with each other, that means that if they both go up and down at the same time by the same amount. Right? They're perfect copies of each other, basically. If the value is exactly -1, they're perfectly negatively related. So if one goes up, the other always goes down. Right? There's always a negative relationship. And then there's the 0 in the middle. That means that they're not linear related at all. Maybe we should highlight this, the word linear here. Because the correlation coefficient does not catch any kind of relationship, only linear relationships. Maybe to give you an example of what's meant here, so look at the two variables, or at the correlation between the following two variables. The first variable is x, the second variable is x squared. All right, so you can plug in any number for x and any number for x squared. So you see that it's a perfect relationship between the two. When I know x, I can compute x squared from this. Suppose this is a distribution that's centered around 0. That's an assumption that we need. What's the correlation coefficient of this? Between two variables x and x squared. How many zeros? That's a good answer. It's exactly 0. And that's surprising because, I mean, we know x squared when we know x, right? So they're perfectly related to each other. They're just not linear related to each other. There's a squared in it, and it's a quadratic function. Quadratic functions are not linear functions, right? So look at the following. So if you put in some numbers here, say 1, and this is going to be 1. Right? If this is 2, this is going to be 4. If this is 3, this is going to be 9. Right? So they're both positively related. But you can plug in negative numbers as well. Right? If this is -1, this becomes +1. -2 becomes +4. So suddenly in the negative range of values, they're negatively related. Right? If you have a distribution centered around 0, the negative part exactly offsets the positive part. Right? So there's a perfect relationship in the formulas, but it's not caught by the correlation coefficient. It only measures linear relationships. Right? Linear means that, like in the picture of the beta in the scatter plot, you can draw a line, a regression line through it. Right? And if you did that with a parabol, right, the line will be flat. Right? And then you wouldn't find a correlation. Right, just as a side note, we're just looking at linear relationships here, right, which is good enough for our purpose. Okay, so that's just a definition. We standardize the correlation, the covariance to be over the interval from -1 to +1. So the exact positive values, +1, -1, are very rarely observed. If you find relationships in the data around maybe 0.5, 0.6, that's already quite good. So for those of you who have already had in statistics class, this number here is related to a very important measure in regressions, called the R-squared, or coefficient of determination. In German you would say Bestimmtheitsmaß. So R-squared is literally just this number squared. Right? So if you square this number, you get to the R-squared. The R-squared has an interpretation that's pretty useful. It tells you how much of the variation in one variable is explained by the variation in the other variable in percent. Right, so you have a number between 0 and 100%. So if the R-squared is 100%, it means that all the variation in one variable is explained by the other variable. And for the relationship between two variables, it's just the correlation coefficient squared. Right? R-squared is the abbreviation. If you run statistics programs, they will automatically compute this for you. Good. So now the correlation coefficient that we've defined like this appears here in our formula for the portfolio volatility. Start with the portfolio variance up here. So the portfolio variance comprises of three components. The first one is the coming from the variance of the first asset, right? It's the W1 squared times sigma 1 squared. Now if you wonder why these are squared numbers, again there's a rule in statistics that the variance of W1 times R1 is going to be equal to W1 squared times the variance of R1. I think that's one of the formulas I don't have on the slides. But if you take a constant out of the variance, you need to square that. While for the covariance in the expected value, you don't have to square it. So that's where the square comes from. Now we have a term for the second stock, W2 squared times sigma 2 squared. That's this part. And now we have a third term that looks a bit awkward because there's, first of all, there's a number 2 in there. And then we have the product of the portfolio weights, the product of the individual volatilities, and the correlation coefficient. So this is now a term that depends on the sign. So these numbers are usually all positive. Well, for the portfolio weights, there can be negatives around here, but in the example that we have, W1, W2 are positive. And the correlation coefficient now can be positive or negative. And that kind of drives now whether your volatility goes up. If the correlation coefficient is positive, you increase the variance of the portfolio. If this is a negative number, you are able to decrease the variance of the portfolio. And as we've already seen in the data, we expect that the correlation coefficient is negative between the two stocks that we have, and such that we have a risk-reducing effect. If you prefer to use this formula here using the covariances, actually the last part here, that's equal to the covariance between the two stocks. So you could write down the formula with the covariance. However, this expression that I have on the slide here is more often used in practice, because the correlation coefficient has a nice way of interpretation, right? You know that it must be in this range of values. And for covariance, it's difficult to interpret that because it depends on kind of where the share price, for example, is. Good. So these are just basically two formulas that you have to kind of get used to and apply a couple of times to get familiar with them. So maybe let's do this in our particular example. So the first thing I would like you to do is to compute the correlation coefficient between the two stocks. So apply this formula here. Remember the sigma k and sigma j we've already computed, right? So this was 19.1%, this was 22%. And the covariance is a formula that we've studied last week, right? So you know how to compute covariances. Right? But instead of computing the covariance with the market, now you're computing the covariance between two stocks. And then you get a number for the correlation coefficient. You supposedly or expect this to be a negative number. And then you can apply this formula. Again, you know the W's, you know the individual sigmas. So the only one missing here is the correlation coefficient that you don't have yet. So I'll give you some time to try this out. Maybe 7 or 8 minutes since the correlation coefficient probably takes a little bit of time, and then we're going to do the results together. So let me go back to this slide here. So this slide has all the data on it that you need. Right? So these returns you need, and the probabilities you need for the covariance, and these are the individual sigmas here, sigma 1, sigma 2. Any questions? Okay, so let's get to work.